Hey there, folks. Good to be with you again. Today we're going to talk about tangent lines, and I hate to go off on a tangent here, but I'm about to go off on a tangent. Okay, you might want to, I was going to say you might want to have a ruler, but if you have any kind of straight edge, you'll be good. We're not going to use it that much, but maybe just a little bit. But here, let's just quickly talk about what a tangent line is. We've got one right here. So this right here is a tangent line. And what we see is that this line, it touches the circle. It touches the circle at exactly 1 point, no more than 1 point. So I'll just quickly define it as it's a line that intersects the circle in exactly 1 point. Okay, and then that point where it intersects the circle, we call that point the point of, yes, I heard you, tangency. All right, and then the first theorem that we're going to talk about, and we did touch on this in class, so it's kind of just a refresher, is that if you have a tangent line and then a point of tangency, if you draw a radius to that point of tangency, the radius and the tangent line are going to be perpendicular. Okay, so if we put that into an if-then statement, if line AB, in this case, is tangent to, this is circle O, the center is O, and at P, tangency. Then what have we got? We've got radius OP is perpendicular to line AB. Okay? And then the next theorem here is just the converse of that. And if you remember, converse is just basically switching your hypothesis and conclusion. So we're switching around the if and the then. And so if we're given at the beginning that line AB is perpendicular to this radius OP at that endpoint of the radius at P, then what have we got? We've got that AB, line AB, is in fact a tangent. Now this was assuming that we didn't know this was a tangent line in the first place. So it is tangent to circle O, okay? If the radius and that line is perpendicular at the end point of the radius, then that must be a tangent line. So let's stick with that. Let's go to this first problem right here. Hopefully this won't be too tough, because they tell us ML and MN are tangent to circle O. So what is the value of X? X is this angle down here. What is the value of this? If you feel like you've got a handle, go ahead and pause and try to do this on your own. I will continue on. Well, what do we know? If you look at this shape, look at the shape that we have here. L to M to N to O, that's a quadrilateral. So LMNO is a quadrilateral. And what do we know about quadrilaterals? Well, in this case, we care about angles. So what do we know about the angles of a quadrilateral? Well, they add up to 360 degrees. That's basically what I'm trying to say there. Well, we also know that ML and MN are tangents. And we've got these radii, OL and ON. So what must be the case based on the theorems we were just talking about, especially this first theorem? We've got some right angles here. So that's really nice. It's like they're handing us the answer, basically, because now it's just some basic arithmetic, some basic algebra. So let's just add all of these up. We've got angle L is 90. Angle M is, I don't know. I don't know right now, but I will know soon. And then we've got, so this was angle L plus angle M plus angle N plus this last angle, angle O, that's 117. All of that equals 360. Oh man, I was really hoping my equal signs would line up. Oh well. So this isn't too bad, right? If you add up 90 and 117, you get 297. And then bring the x down, x plus 297 equals 360. Do a quick subtraction. We've got x equals 63 degrees. Not bad. And not too tough. Oops, sorry, let me slide that up some more. Hopefully you caught all that. And next, I'm going to move on to, oh, I really like this next problem. It's not because I'm from Toronto, Canada or anything. I'm not. It's a nice place. I think I've been there once, but it's just, this is just cool because we've got this tower, the CN tower. What does CN stand for? I don't know. Look it up. It has an observation deck at about 447 meters above ground level. That's pretty tall. How far is that? How far is it from the observation deck right here out to the horizon? So it's like if you were standing up here on the observation deck and you were looking out into the horizon, doesn't that just sound so like dreamy and wistful? You're looking out into the horizon. How far could you see? Right? How far out are you looking? So let's, this circle here is, yep, you guessed it, that's the Earth. And just to kind of remind us, there you go, that's Earth. Let's draw in some stuff here. Let's draw in the tower on the Earth. Wait, hold on, I gotta draw very carefully. There you go, boom, that's the tower. And then there you are on the observation deck. Say hello. And what's the length of this little segment? Well, they told us 447 meters. Oh, by the way, I like this little bit. Look at that. The Earth's radius, 6,400 kilometers. This is kilometers. This is meters. I think we should like reconcile these units. So off to the side here, we've got 447 meters, and let's put that into kilometers. I didn't leave myself enough space. Oh well, I think I'll be okay. What do we multiply this meters by? Well, here's what I like to do. I like to think, well, I'm going to multiply by some fraction. I want to end up with kilometers, and I want to get rid of meters. Well, I'm going to multiply it by a fraction where meters are on the bottom, kilometers are on the top, because the meters are going to end up canceling, and the kilometers will stay. So what's the relationship here between kilometers and meters? Well, 1 kilometer makes 1,000 meters. It's a good fact to know. So we're essentially going to multiply 447 by 1 over 1,000, or divide 447 by 1,000, and we get 0.447 kilometers. That might have been really easy for you, but I just wanted to do this little unit discussion. So we've got that little segment is 0.447 kilometers. And then I guess here's where the ruler is going to come in. Let's just get the center. Yeah, sure, that's the center. Ooh, I was hoping that would be a straight line. Yeah, it sort of works. And then let's draw the radius of the Earth. What's that radius? They told us 6,400 kilometers, not drawn to scale, clearly. This is 6,400, that's like 0.447. Again, not drawn to scale. Oh well. Now, but if you're standing up here and you're looking out over the horizon, can you imagine that? Let's say you're looking in this direction. What is your line of sight there? Your line of sight, I hope you realize, is actually going to be, let's just draw it in. It's going to be a tangent line. So let's draw that tangent line in there. I'm trying to get this just right so it's not that big a deal, but whatever. Something like that. This is where you can see, right? That's your line of sight. So you can see about to that point on the Earth and no further. You can't see what's going on over here on this side of the curve, but you can see like up to here. So let's we said that's the point of tangency. Let's draw another radius to that point of tangency. Do you see what's happening? Can you kind of sense like what's going to happen? Ooh, yeah. See that's, and what's the length of that radius? That's 6,400. And what's going on over here? Remember, radius, tangent line, radius to the point of tangency. We've got a right angle, folks. That's pretty exciting. And so, and let's throw on some letters to represent these points. I'll call this T for tower. Let's call that E for Earth. And then C for center. All right. And what do we want? We want ET, right? We want ET to come home to us. Okay, hopefully that you get that joke. Maybe not. How do we get it? Well, we've got a right triangle here. Hopefully you see that. So let's do this. Let's use something our friend Pythagoras gave us, the Pythagorean theorem. What would that look like? That would look like ET squared, that's the one we want, plus EC squared, ooh, we know that, equals, maybe I'll give myself a little more space, CT squared, and we know that as well. So let's now plug stuff in. EC, we've got 6,400, so we're going to square that. CT, oh, we just add those two. It's 6,400 plus 0.447. So 6,400, 0.447 squared. And I'll just bring down the ET squared. We don't know what that is yet. Let me just do this really quickly in my head. 6,400 squared, that's 40,900,000. Yeah, okay, that's right, 960,000. I just checked it in my head, that's true. And then this one, this is even easier to do in my head. That's going to be 40,965,721. 0.8. Silly, I almost forgot the 0.8. Now bring down the ET squared. Now we're just solving stuff. This is easy to subtract, actually. You can almost don't even have to use a calculator. So we've got ET squared equals 5,721.8. Square root both sides. Here it is, 75.6. And we're dealing with kilometers, so that's how far you can see from that beautiful observation deck. So while you finish imagining that, and maybe take a trip to Toronto and then come back for the next video.